Okay, wonderful. So, okay, so what we're gonna do is today in this workshop, we'll learn. So I will be mostly writing on the tablet. Okay, so no slides. I may show you some code, but there are no slides essentially. So we're gonna study logic programming plus Prolog. So Prolog is a logic programming language, and some of you may have taken CS4337 programming languages, and you may have come across Prolog. But nevertheless, it's good to go through a refresher. And then in the next workshop, we'll see how we add features to Prolog to obtain what's called answer set programming. And then we will use answer set programming for automating common sense reasoning. So Prolog itself, logic programming itself, lets you automate reasoning. Why? Because Prolog and logic programming are based on logic, and logic is important for reasoning. Can you hear me?
I can hear you, yeah.
Okay, awesome, thanks. So logic programming and Prolog are used for reasoning, and reasoning is based on logic, and these paradigms or logic programming paradigm is based on logic. So we'll see how we can automate common sense reasoning, and why that is important. It's because, you know, our day-to-day thinking is based on, our thought process is based on common sense reasoning. I mean, we call it common sense reasoning. So we'll see how we can actually simulate the human thought process. And if we can emulate the human thought process, then we can pretty much automate anything, right? That's the premise on which all this is based. So to understand answer set programming, first we have to understand logic programming. Okay, so and logic programming, Prolog is a very sophisticated language. Okay, so let's get started by um, looking how we will represent a family. So start with a very simple example. How would we represent a family database in Prolog? So let's look at a family tree. So we've got two individuals, Lisa and Tony, and they have two children, Abe and Sarah. So Lisa is the mother of Abe and mother of Sarah, and Tony is the father of Abe and Sarah. And Abe has John as a child, and John's mother is Nancy, and Sarah has Susan as a daughter. And so you can see it's a family tree. Jill and Mary, and then Susan has two children, Jack and Phil, and Rob is the father of the two, and so on. So what we want to do is to represent this information in logic. So if you look at a Prolog program, it consists of facts. And what are facts? Facts are unconditional truths. If you have any question, then questions, then just raise your hand and ask. So facts. So essentially, facts, right, as the name denotes, these are things that you know. So for example, Lisa is the mother of Sarah is a fact. Then you have rules. And rules you can think of as conditional truths. So these are things that you want to establish but their truth value or these uh, these predicates or these relations depend on other predicates being true. So facts and rules, they all are built using what are called predicates. And what are predicates? Predicates are nothing but a relation. So for example, if you say father Tony, comma Abe, then father is a predicate. And predicates from your discrete math or from your any of your computer science classes, they evaluate to true or false. So either Tony is the father of Abe. If Tony is the father of Abe, then father Tony, comma Abe predicate holds is true. Otherwise, it will be false. So then you use facts, predicates that define facts to establish other predicates, and you use rules for that purpose. Okay, so I'll give you examples in a little bit. And then finally, you have queries. So once you have facts and rules, then we want to use these facts and rules. So that's a collection of facts and rules is a logic program. And then we want to take this program and compute things with it. So for example, if I have this family database, I might define the father relation and the mother relation, and those will be facts. But then I might define grandfather relationship or grandmother relationship or grandparent relationship in terms of father and mother relationship. And then I might define more complicated relationships such as ancestor relationship or uncle or niece or nephew. So those relationships will be defined in terms of the basic facts that we are given about father and mother. Okay. So once you have the program, then you can query it. So I want to compute, for example, if Lisa is the ancestor of Jack, I should be able to compute that information from facts and rules. Okay. So let's start. Okay, so it's a little bit warm in this room with two computers running. So let me just turn on the fan. Okay. Okay, so let's erase this part. So, okay, so we have facts and rules, and we have queries. So let's look at examples of facts and rules in our family database. Okay, so I will write father Tony, comma Abe, and end it with a period. So that's a fact. So I'm stating unconditionally that Tony is the father of Abe. And then you can see that every link will turn into a fact. So it's actually Prolog syntax. So in Prolog, constants strings start with a lowercase letter and variables begin with an uppercase letter. So that's why even though Tony and Abe are proper names, I'm writing them with lowercase letters. Okay. So let's write the rest of the database, father Tony, comma Abe, father Abe, comma John, father Tony, comma Sarah, obviously, right? Father Abe, comma John, father Bill, comma Susan, and all these names will begin with a lowercase. Father Rob, comma Jack, and father Rob, comma Phil. Have father John, comma Jill. Correct. So for each link in the graph, right, I will have a relation. So predicates are nothing but relations, really. So what you're really saying is Tony and Abe are related to each other through the father relationship. Okay, or you can write it as a predicate stating father Tony, comma Abe holds. Okay, so let's write the mother relationships. So we have mother Lisa, comma Abe, mother Lisa, comma Sarah, right? And you can see that even though, from the name we can tell the gender, but when you write things in logic, logic will not know anything about anyone's gender. But by using father and mother relationship, right, specific relations, we're kind of encoding this gender information. Nancy, comma John, mother Nancy, comma John, mother Mary, comma Jill, right? So far so good. Then mother Sarah, comma Susan, and all facts end in a period. So you see this full stop. And then mother Susan, comma Jack, mother Susan, comma Phil. So let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 facts. And are there 14 links? Yes, there are 4 over here, 4 over there, and then 6. So total of 14 links and 14 facts. And now that I have the family database described as facts, I can start writing rules. So a very simple rule that I can define the parent relation. So I could say X. So now we start using variables. We say X is the parent of Y. So also notice that we said Tony is the father of Abe. So we're assuming that the first argument of the predicate father denotes the father and the second argument denotes the son or the child or the daughter, right? So we could have used any convention, but so you're free to use any convention you want. You can denote first argument, right? When I say first argument, I mean you all understand what a predicate argument is. So I could have written father Abe, comma Tony to mean the same thing. But once you use a convention, you have to stick to it. So we'll keep using the senior person as the first argument and the junior person as the second argument. So X is the parent of Y. So any guesses? So this colon dash means if. So X is the parent of Y if, so this is, we're now writing rules. If father X, comma Y. Now we can define parent using 2 rules, right? And now you guessed the second rule already, right? It's mother X, comma Y. So X is the parent of Y if mother X, comma Y. And now we can write the grandparent relationship. We can define who's grandparent of who. So now you probably can, okay, well, I still need to tell you a little bit more machinery. So grandparent is X is the grandparent of Y if okay, starts sometimes, yeah, it just misbehaves. If X is a parent of some Z that I don't know who that Z is, and comma means and what can you say about Z and Y, right? You guessed it almost. Parent Z, comma Y, right? So you see, you can define the grandparent relationship as GP X, comma Y, if parent X, comma Z, comma, which means and parent Z, comma Y. And you can think of the if as an, so when I write parent, or sorry, grandparent. So we'll see how essentially logic programming is about using logic as a programming language. Okay, so and you can see how straightforward the rules are, right? You can write these rules in a straightforward way. So learning it is not very hard, but as you know, with programming, right, when you have to program complicated things, and your program can become complex. But the syntax and the semantics, the meaning of programs is really straightforward. So GP x comma y if, so let's write. So this if is nothing but an implication in this direction. Those of you who've taken propositional logic or predicate logic, right, have seen A implies B, right? This stands for, you can think of this as B holds if A holds, or if A holds then B, if A then B. So many ways of writing this. Okay, so when you write a rule in Prolog, you're saying GPX comma Y is implied by, and you can think of this arrow in the left direction as an if parent x comma z and parent z comma y. So what we're really doing is we're writing formulas in logic, except that we'll see that these formulas in logic have a computation interpretation. So we can actually execute them. Okay, there's a hand up. Yes, please go ahead.
Professor, good afternoon. My question is regarding the parent rule that we just created. Is can we create a disjunction of facts for a
Yeah,
row
you
of
can create
equations?
disjunction. We'll come to that later. Yes, yeah. So good question. Yes, you can create. So there is a semicolon that you can write. So we could have written parent x comma y if father x comma y semicolon is an or. But generally, you don't want to use too much of semicolon except for improving readability, because you know if you mix up semicolon and comma, rule can become confusing to read. So the program will become less readable, but it's definitely is there. And what the compiler will do is actually take a rule like this and transform it to what you saw in the previous page. It will transform it into this. Okay, but there is a semicolon that you
Okay,
can
thank
use
you.
to denote R. Yeah, sure. But it's not essential to use semicolon, as you saw, because I can write two rules. And so the interesting thing is that so you can interpret these as procedures. So you see that you have not come across a programming language where we'll see that where you have multiple procedures to define a given concept, a given, in this case, predicates or a given function. Now you do have, in other languages, you can have multiple definitions, but you have to make sure that through, typing constraints of arguments, only one procedure applies. In Prolog, we'll see that if we have a call and we have a matching procedure, we'll try that procedure. If that doesn't work, we'll try the second one and third one and so on. Okay, but we'll see as we go along. Okay, so you can read these rules as formulas in logic. Parent x comma z and parent z comma y implies GP x comma y. And now I can define great grandparent x comma y if, and now since we have GP, we can make use of it. So we can write GP, find the grandchild of z, of x, namely z. And then what can you say about z and y? Anyone? Comma means and. Z must be parent of y, right? So then I can build great great grandparent and great 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 grandparent. And then you notice that I could have written this in another way too, right? I could have written this as x is the great grandparent of y if the child of x is z. So z is the child of x, and in turn, z is the grandparent of y, right? So there are two ways of defining it. Doesn't matter which one you use. And I can build now great-great-grandparent. So you can define rules and then use these rules to build more complicated rules. Okay. But now suppose I want to define ancestor, that X is the ancestor of Y. So X is the ancestor of Y. How do you do that? So for example, I want to establish Lisa is the ancestor of Jill. Then if you were to write a program for this, then you will say, oh, let's start with Jill, find her parents, and then find parents of parent and parent of parent until we reach Lisa. So we'll basically write a while loop type of thing, right? But interestingly, in Prolog and in logic programming, there is no while loop. If you want to write an iterative program where you're doing something repeatedly, you have to use recursion. So let's see how we can write define the ancestor program. But okay, before we go there, let's see now that we have this simple program where we can compute parent of an individual and grandparent and great grandparent. How do we execute this program? Okay, so let's look at that. Now, notice also one more thing, that moment we define a relation, for example, parent, we also define the inverse relation, right? The moment we define that when we say X is the parent of Y, right, in this rule, we're also defining that Y is the child of X. So moment you define a predicate or a relation, its inverse is automatically defined, right? So when I say, when I define grandparent, X is the grandparent of Y, then automatically grandchild relationship is defined as well, right? So what I can do now is I can execute these programs. So how do we execute these programs? So let's add another page. And so we'll do a query will always be preceded by, okay, so on, so the best thing to execute Prolog program is to use SWI Prolog. It's free Prolog that's available. Just Google it and download if you want. Or if you go to our Linux machines at UTD, like CS Linux 1, I think you all have access to that, I believe. Then at the prompt, if you simply say SWIPL, and I'll show you the execution, then it will give you a prompt saying, okay, I'm ready to listen to your queries. So first thing you may have to do is to load the program. So you load your program by saying consult. Let's say we saved our program in a file called family. Let's shorten it to FAM. So I could simply, or fam.pl. So .pl is the Prolog extension that you can use. But you can use any extension you want as long as you give the full path name of the file or the file name. So I could, for example, say within quotes .pl, since we're using a special character, right, parentheses and a period. Everything in Prolog ends in a period, okay? So even these rules, where did we? So this rule also ends in a period, okay? So everything in Prolog ends in a period. Okay, so at the question mark prompt, I can say, or at the prompt, I can put a query. I can, for example, say, I can simply check, is Lisa the parent of Abe? So I can, and period again, remember? Let's just move it away a little bit further. And you can see that the answer will be yes, but how is that answer computed? So it will say, okay, let's find a matching rule. Matching rule meaning the head of the rule. So this part is called the head. And everything to the right of the colon dash is called the body. Okay, body. Or let's go to page number 2. So this part is the body. Let's get the green pen since I have it. This part is the body. And this part is the head. And obviously then this is the neck of the class. Well, but neck doesn't have much significance. Okay, so okay, so it sees the call. So think of this as a call. Query is basically a call. I want to solve for parent Lisa, comma Abe. I want to establish that the predicate Lisa is the parent of Abe is true. So Prolog interpreter will go and try to find rules that will match, the head of the rule will match the call. So in this case, since X and Y are variables, they have no values, so they're like wild cards, so they can match anything. So it'll say, oh, let's try the first rule. Okay, so it'll say, let's try the first rule. So you have formal parameters X and Y. X gets bound to Lisa and Y gets bound to Abe. And then you replace it with, right, with the body of the rule. So father, X comma Y, Lisa comma Abe. But you see now what will happen, that we don't have, so father is a fact, right? So it knows that father is a fact. Father is a fact. But it tries to match it up and finds that there is no father fact with Lisa in the first argument. So it fails. So it's failed to prove that Lisa is the parent of Abe. Okay. So when we actually execute in logic programming and Prolog, we're actually proving things. Okay. So we failed to prove that Lisa is the parent of Abe. So what will Prolog do? Say, okay, well, we had another rule to try. So let's go up the chain and see if there were multiple matching rules, and it will remember that, oh, there was an untried rule here, untried alternative rule. It'll go up, and this process is called backtracking. So it will backtrack up the stack, up the execution chain, and find a point where there's another thing that can be tried. Says, oh, there is another rule, let's try that rule. And now when you backtrack, everything is undone. So the bindings of X and Y are removed. It's as if you restarted the execution from here. And now to try the second rule and say, okay, let's bind X to Lisa. Let's bind Y to Abe. And now we have to solve X is Lisa, right? Mother X comma Y, replace it with the body of the clause. And now we'll find a matching fact. So it'll say, success, and print the answer, which will be yes. Okay. So we executed our first query, so which is just checking that Lisa is the parent of Abe. Okay, now let's make it a little bit more interesting, and let's say we leave something, we really never computed anything. We're just kind of checking that Lisa is which is great, you can do that. Okay, now we can say, we can say, okay, who is the parent of Abe? So I can put the variable X and say, give me an X such that X is the parent of Abe. Now, one more thing I should mention is that when we write rules like this, for example, we wrote this grandparent, this rule, right? Then these variables X and Y are universally quantified, which really means this is the formula for all X, for all Y, for every Z, grandparent X comma Y holds if parent X comma Z holds and parent Z comma Y holds. Okay, so all the variables in any rules are universally quantified. You're basically saying for every X, for every Y, for every Z, for every whatever, this relationship holds. Okay. So here we're saying, but here now we're saying, is there an X? So the variable in a query is existentially quantified. Is there an X? Does there exist an X such that parent X comma Abe? And now again, Prolog will start the same way, say, okay, let's match the first rule, and we get, let's call this A. I mean, you could use X because Prolog will rename all the variables to distinguish formals from the actuals. So you say parent A comma Abe, and it'll say, okay, match the first argument. So A and X must be, now you notice that A is unbound, A is unknown. We don't know what A is. And if we look at the at the rule, X and the formal parameters X and Y are also unbound. So basically what we're saying is A and X are alias. Whatever value A has, X must have the same value, but Y can be bound to Abe. And my next call is using the first rule. So we'll try the rules top to bottom in textual order. So we'll try the father rule first and the mother rule next if father rule doesn't work out. So we say, okay, parent A comma Abe, father X comma Y, which means replace X and Y with their actual values. A is X, sorry, X is A and Y is Abe. And now we say, oh, we have to now execute father A comma A, but now we get lucky because father A comma A, yeah, we find a match, right? There is a fact where A can match anything, right? Because it's unbound. So it matches Tony and second argument has to match the string Abe. So it'll come back and say A equals Tony. At this point, you can accept this solution, or you can say, oh, and which if you want to accept the solution, you'll type return and you'll get the question mark prompt back again. If you don't like this solution, then you will hit semicolon. Semicolon will force it to backtrack. So it will backtrack and again, it will undo everything up to this point. And now it'll try the second rule and it'll say, okay, A and X in the second rule are aliased. Y is bound to Abe. But now I got the call mother X comma Abe. And now you see that there's another, right? Because Abe has not only has a father, but also has a mother, and mother is parent also. So it'll match this fact. And now you will get A equals Lisa. And you got your second answer. Now again, if you hit semicolon, there are no more answers and it'll say no and give you the question mark prompt back. Okay, so that's how you execute programs. And basically the call execution is essentially start with the call, find the matching rule, the first matching rule, match the arguments. The arguments may bind some variables. Then you replace the call with the body of the matching rule, and you start executing the calls in the body in a similar manner. Okay. Now I could have also asked the query. So see, here we wanted to compute the parent, but we could have also have asked the query, tell me the children of Lisa. And it will follow the same process and tell you the two children of Lisa. And those are Abe and Sarah. And you can try all this out. So type up this program and then try it out on SWI Prolog. Okay. So here now you will get, first we'll get answer B equals Abe. And if you hit semicolon, it will come back and tell you B equals Sarah. Okay, so now we can try the grandparent. So we can say, oh, we could also have said the following. We could actually have left both unbound. And you tell me what will happen then. If I say parent A comma B, what do you think will happen? I say, well, any guesses? It'll basically go through, it'll give you every mother, father, parent comma child pair. So you will get 14 answers. As you keep hitting semicolon, you'll get answers one by one. So it's a wonderful language for programming databases. And you can see that it's a lot easier to write Prolog programs than to write SQL programs. Those of you who are exposed to databases and have written SQL code. Okay, so let's go. So you can see that programs, I mean, as I said, parent, when moment you define a parent, you also define the child relation. And likewise, when you define a grandparent, you define the grandchild relation. So let's see, we go to our tree and let's see. I want to know if Abe is the grandparent of Jill. Abe, comma, Jill. And now what will happen? First, there is only one rule. So GP Abe, comma, Jill will be expanded into X, right? We look at our rule for GP. GP X, comma, Y, parent X, comma, Z, parent Z. So X, comma, Y are the arguments. So X becomes Abe and Y becomes Jill. And now let's see the body, the call for GP X, comma, Y will be GP whatever will be replaced by the body. And so now this will be replaced by parent X, which is Abe, comma, Z we don't know, so we write it as it is. And then parent Z, comma, Jill. Right? So what now we have two goals, two predicates to solve for. So we'll solve the left one first, and then once we are done with that, we'll come to the right one. Okay. So you execute left to right. So if you have sequence of calls, you will execute them left to right. You could have executed them right to left as well. So that's a nice thing about Prolog. So notice there is no assignment statement. There is no such thing as saying, well, so far, you cannot say x equals x assigned for x equals 5, like in C, which binds x to 5. You can't do that in, I mean, you can, but then you cannot say x assigned 5 and then x assigned 3. Once you fix the value of a variable in Prolog, it stays the same forever. So x equals 5, x equals 3 will produce an inconsistency, your computation will fail. It will. So basically variables are like mathematical variables that you see when you in algebra. Right? In algebra, you don't have variables that can take different values at different times. So variable stands for a specific value. Once that value is computed and given, that's it. It stays that way. If you want to compute something else, so for example, if you want to set x to x minus 2, right? In C, you will write x assigned x minus 2. But in Prolog, you'll have to use another variable name, and you'll have to say y is assigned x minus 2. Where this equal is actually the unification operator, but we'll learn more of that in a little bit. But so far so good, right? You can follow what's going on. So let's start executing left to right, parent Abe, comma, Z. So now you can see that Abe, comma, Z will match. There are two possibilities, right? And I'll skip some steps. So father Abe, comma, Z. And what you do is you copy rest of the calls. Once I'm done with father Abe, comma, Z, so that I don't to go back once I'm done with the calls. I'll copy this part. So that once I solve for when father Abe, comma, Z is done, I can just go straight to, and this is still untried alternative. Now I can see that father Abe, comma, Z will produce. What will Z get bound to? Anybody? Okay, John. Yes, very good, because Abe is the father of John. Excellent. So Z equals John. But now Z gets bound to John. Remember that a variable, once it's bound for good. So my next call will be parent John, Jill, which is exactly what you wanted, right? Once you computed the child of Abe, you want to see if a child of Abe is a parent of Jill or not. And now again, two alternatives. And then you will see that parent John, Jill is indeed true. Well, I mean, this will become, so I'm going to skip some steps. Father John, Jill. And then you can see that Father John, Jill. Oh, he doesn't have a name. Okay, Father John, Jill is there, so that this is a yes. And I am done with showing that Abe is the grandparent of Jill. Success. Now, if I hit semicolon, it will go backtrack and try this branch, and it will probably fail because mother John, Jill will fail, and then it will go further up and try this branch, and this time it will say mother Abe, Z, parent Z, Jill, and then mother Abe, Z will fail because Abe, I mean, there is no such fact. So you can see that kind of we build a search tree, right? So sort of there's a search tree, and we're searching for a solution in a depth first manner. So searching for a solution in a depth first manner. So we're really doing a depth first search of this tree. Okay, so hopefully you get an idea as to how execution is taking place. And I'll show you some sample runs. I will log on to SWI Prolog and I will show you some code running. Okay, any questions? So, if you have any questions, do put them on the chat. Oh, okay, sorry, I see there are some questions. Okay, so somebody asked, can you do ggpx, y, parent x? Yes, you can do that. Parent x, z, parent z, w, parent w, y. Yes. So you can define the whole parent chain. Indeed. Another question, are all the father and mother functions given statements? Yes, we assume that all that data is given to us. So for example, if you ask if Sam is the father of Jane, and I have no information about Sam and Jane, even though Sam may be the father of Jane, the system is going to say no. So you assume that whatever is given to you is the only thing known. And then there's a question, what is the percent? Percent dot. Oh, percent dot was the Unix prompt. So, right, so on Unix, generally you will get some kind of prompt. So percent is a Unix prompt. So you type the command swipl, SWIPL, right? So it's basically command line Unix is what I'm talking about. Okay. So command line Unix, then you just type the command SWIPL, and then hopefully most of you are familiar with it. But in any case, if once you download SWI Prolog and install it, then you can just run it by I mean, it's there as an executable, right? You'll have the icon, you open it up, and it will give you the question mark interface. So I generally use Unix machines for all this kind of stuff, but it's really straightforward to use, and you should try it. Okay, so any more questions? Okay, all right, let's go to okay, so now let's see how we can write loops or recursive programs. So now I want to define the ancestor relation. Okay. So the ancestor relation will have to be defined recursively. So how will you define ancestor? X is the ancestor of Y if, so who's an ancestor? A parent is an ancestor, right? And then we'll define another rule that says, what if I'm, so parent is one ancestor, but there are other ancestors also. And those are grandparents, great-grandparents, great-great, and so on. So what we'll say is, okay, X is the ancestor of Y if X is the parent of Y, or X is the ancestor of Y if we find the child of X, namely Y, and recursively establish that Y is the ancestor of Z. Okay, so this is like saying I have X over here and Y, and in between there are lots of individuals, and then I might have a database family tree, which is complicated. So what we're saying is that I want to establish X is the ancestor of Y. So find the child of, namely Z, right? This is Z. And then recursively, you can see that Z is the ancestor of Y. So when you make the recursive call, again, you'll do the same thing. Say, okay, let's find the child of Z, namely whatever Z prime, and establish that Z prime is the ancestor of Y. So what you're really doing is sort of walking towards the descendant. Okay. But logically, so when you write recursive programs in Prolog, don't think in terms of, operationally, think in terms of logic, right? So you can see logically is very clear. X is the ancestor of Y if X is the parent of Y, and X is the ancestor of Y if, sorry, I messed up here. This should be Z and this should be, find the individual Z, and Z is the ancestor of Y, right? So X is the ancestor of Y. If I can find a Z such that Z is the child of X, and recursively Z is the ancestor of Y. Okay? Make sense? Yeah, okay. So I think somebody already pointed out. Thank you. So ancestor X comma Y if parent X comma Z. So you can see logically it makes sense. So you can write recursive rules, and there's no problem in writing recursive rules. Just make sure that your recursive call is not the very first thing, because sometimes that can cause trouble. Go into an infinite loop, even though it's a logically correct program. Okay, so now I can say ancestor, let's see, is Lisa the ancestor of Jill? Okay, so again, we'll do the same thing. We'll first try the first rule. X becomes Lisa, Y becomes Jill. And then we replace by parent Lisa, comma Jill. And then this will reduce to father and mother, right? But you can see that Lisa is not the direct parent of Jill. So this will eventually fail. And then you go back and expand using the second rule. And now you will get parent Lisa, comma Z, comma ancestor Z, comma Jill. And now you will compute the value of Z. You will find out that Z is one of the two. Z is either Abe or Sarah. And the fact that Jill is a descendant of Lisa could be found through Abe or could be found through Sarah. Right? So, and then you keep tracing and you can see that you will actually get the answer. Okay, make sense? So let's see, let me quickly, okay, maybe I'll run other programs. Okay, so now we can take a database type of information, express it as relations, and then we can query it. So we roughly know how to do that. Now, if you there are a lot of resources available. I think there is a free book available called The Art of Prolog. I mean, it used to be not free, but I've seen its PDF copy on the internet. Seems to be a legal one. The Art of Prolog by Leon Sterling and Ehud Shapiro. So you can read the first few chapters from there, which is what I'm covering really. There are lots of tutorials on Prolog that you can find online. But remember that eventually we want to learn answer set programming and how to. So for the HackReason, as long as you can do database programming of this kind, you should be okay. And you see that, right? You can see that it's not really that complicated. But well, at least when you writing the program, but then when you execute it and figuring out what your program is doing, may not be as straightforward. Okay, so next thing we're going to do is what about data structures in Prolog? How do we write sort, and how do we represent data and all those things, right? So let's see data structure. So or let's see how we add data structures to Prolog. So the main data structure that is used in Prolog is a list. And I mean, so I teach this class on computational logic, so you can have a whole course around logic programming and Prolog. But the idea is to get you enough information so that you can code and you can maybe make build some interesting application during the hackathon. So it's not the I mean, as long as you have basic, ability to write some code, and there'll be people there to help you, execute your code and things like that. About half dozen people, maybe more. So the idea is to just get a flavor of how to write this code, and do something interesting. Okay, so list. What is a list? I mean, your list from probably your programming data structures class, right? So the list 10, 20, 30. So, right, for example, right? So you'll represent a cell in memory where you will put 10 and a pointer to the next cell, 20, and then 30, and so on, right? And then you have a null pointer at the end. So if you were to program this list in C, you will have to have a bunch of instructions first to build this list on the heap, right? Using malloc or whatever. Or if you in Java, you probably will just create using new or whatever. But in Prolog, you can simply write this list as 10, 20, 30. And it will give you this list without, I mean, it'll just basically do all the memory allocation and setting up automatically. Okay. And then the most important operations in lists are, so operations on list, finding the head of a list, and finding the tail of a list. So head of the list of this list is 10, which is the first element of the list. Tail of the list is rest of the list minus the head. So if L equals 10, 20, 30, then head of the list is, so now remember that there are no functions here. So the way to obtain the head in the list is to pattern match, because everything has to be a predicate. So head vertical bar tail, if I match it with this sequence, so at the prompt, what I'm saying is is H vertical bar T, which really stands for that I have a cell. This field is called H. This field is called T. So head H is the head, T is the tail, right? Head is the value in the first cell, and tail is the value, whatever this pointer points to. So then Prolog will say, okay, H is 10 and T is the list 20, 30. So the tail will always be a list, as you can see. Okay. So now you can represent, cumulative data or aggregate data as lists. That's the only data structure you have pretty much. I mean, there are other data structures, but we will not worry about those. So now we want to be able to manipulate lists. So let's start writing some programs on that you make use of lists. Okay. So the first program that we'll write is to find if an element is present in a list, right? That's what you do, isn't it? In your C class or your data structures class, probably the first program you wrote using lists was locate if an element is present in the list. Okay, but now the code here will be much more succinct because you'll see that in general, when you write in logic, your code is going to be much more concise. Okay, so we know how lists are represented within square brackets, sequence of numbers, and lists will be arguments of predicates. Okay, so let me just write the program for membership. So I'll define rules for checking if an element X is a member of a list L. Okay, in Prolog, if you precede a line in the file with %, it means comment. So member X comma L, which means that X is present as an element in list L. Okay, so how will we define this? So think about if you're given a linked list, how would you find an element in the list where you start from the first element, right? So you'll check that the first element matches your element X. If it matches, we are done. If it does not, then find the tail of the list, right? Use the pointer to skip to the next element and perform the same check again. So you can write a recursive program. So we can say X. Okay, so X is present in a list if my list is of the form X vertical bar L. You see that, right? So this element is X, and my first element of this list, which is in the second argument, is also X. And rest of the list is L, but I don't care about it. But if it doesn't match, it's some other Y, then what will you do? Recursively check if X is present in L. Okay, let's make this T for tail. So you see, so remember we needed a loop, and since we don't have any loops, all we can do is use recursion. So this says X is present in the list if it's present as the head of the list. Otherwise, check that X is present recursively in the tail of the list. Okay, so now how will we execute this program? So you can take this 2-line program and you can actually check. So maybe, let me see if I'm still on. Okay, no, the other way around. Okay, see if I am still logged onto my Unix machine. Okay, yes. Okay, awesome. So you can see that I am on Babbage, which is a Linux box. So let's call it mem.pl. So we create a file called member x comma x vertical bar t, member x comma y vertical bar t, if member x comma t. So it's a very different way of thinking, as you can see. Okay, so we created this program. All right, so okay, so we see this program. Now we invoke SWI Prolog, and then I will say consult mem. Okay, so it gave me some warning signs. It's saying variable t is a singleton, occurs only once in this rule, in the first rule, and variable y occurs only once. It's worried that you might have mistyped. So what we can do is, if a variable occurs only once, it's a good idea to put a x underscore. So we put, say, we don't care. So underscore means don't care. I mean, this variable will occur only once, so I'm not going to pass this value to somebody else. So we'll make it underscore. Okay, and now those warnings will be gone. Okay, so now consult again. Oops. Consult mem. Okay, this time I'll say mem dot give the full name within quotes. Okay, so now see no errors. And now if I say member 10 comma 5, 10, 20, what do you expect? Semicolon means, is there another way of showing that 10 is a member of 5, 10, 20? It says false, no. Now, how do we compute with this? Well, what if we leave things, unbound? What if we say member x comma 5 comma 10 comma 20? What do you expect? Anyone? Make a guess. So it's saying, is there an x such that x is a member of? Yeah, so it will give you first one. So x is 5, you type semicolon, you'll say 10 and say no. Right? So that's the nice thing about logic programming, that basically a single rule encapsulates a lot. And in some sense, when we store our knowledge in our mind, we sort of work in this way, where we look at a relation, and that relation we use for computing forwards and backwards. And it can even do this. It'll say, let's say you say member 5, is 5 a member of a list? It doesn't matter, so that I can use the same 5 comma a comma 20. Any guesses what this will do? So this is saying, is 10 a member of a list which has 3 elements, 5, an unknown element, and 20? So it will say, well, if a is 10, then yes. You see? Right? Isn't that wonderful? Okay, so this is how you compute with lists. So that's the membership query. Now, what about append? Appending two lists. Okay, so now I will have to again go back to the tablet mode and start writing again on OneNote. Okay, so now what about appending two lists? So to append two lists, what you would want is, we want to be able to say append let's say 1, 2, 3, 4, 5, right? So I have two lists, 1, 2, 3, and 4 and 5, and I want the result R. Then it should be able to tell me R equals 1, 2, 3, 4, 5. This is what I want to do. How do you do this in C? You say, okay, let's march down the first list, reach the end. When I reach null, I will replace the null with the pointer to the second list. Isn't it right? Most of you probably have taken data structures, right? So if I have two lists, 1, 2, 3, list call it X, another list call it Y. And so if you were to write a C code, you'll say, oh, let's walk down the first list until we reach the null pointer. And when we reach the null pointer, then copy Y there. And I got this list. And you do something very similar, except that we will think recursively. Okay. So what will be the code for append? We'll say, so, okay, so the list is a recursive data structure, right? Why? Because a list consists of head. So this vertical bar pattern basically matches a list whose head is H and tail is T. So you can see that a list consists of recursively a smaller list T. So it's a recursive data structure. And what is the base case is the empty list. Okay. So for example, going back here, suppose I said, okay, how do I, oh, I can write here. Let's see if that works. No, it's not working. How do I get the keyboard here? Okay, no, it's got the wrong one. Okay, anyway, I'll put the keyboard in. So let's go back to, okay, so the base case will be if my first list is empty. If my first list is empty and the second list is L, what should be the answer of appending L to an empty list? Anyone? Okay. Yeah, very good. Excellent. L. Now take the non-empty case. My list is non-empty, which means it has some head H and some tail T. And my list that I want to append to this list is L. Then we will use recursion now. So think of recursion as magic. Suppose magically I can solve the smaller problem. If I can magically append T and L, so if I can magically take the smaller list and append to it this second list, and suppose that result is called R. So if I magically append the list 4, 5 to the list 2, 3, which is the tail of the list, I will get 2, 3, 4, 5. How will I get my original list? Stick H in front of R. And there's your program for append. Okay, so you see the power of writing programs recursively. You're saying Okay, so I'm explaining this so that if in case you need to use data structures in HackReason like lists, then you can do some programming, but you probably will be able to get away without. But still good to learn this as a computer science, software engineering, computer engineering student to, have this sophistication in thinking. So you see, I can define append very concisely in two cases. Appending L, so remember this is a fact. It's saying it's unconditionally true that L appended to an empty list is L. And appending L to a list whose head is H and whose tail is T is a list whose head is H and rest of the list is R, where R is recursively obtained by appending L to the tail. So you can see that almost your thought process of appending a list is just being written in logic, right? So you see why logic programming is a good paradigm or methodology for capturing the human thought process. Okay, well now this is for lists. Most of the time we'll just capture it for much simpler things like family database, or it'll become more complicated, but we will hopefully will just deal with database type of applications. Okay, so now that we have this, then let's see if we can run. Okay, and then I will show you, well, I mean, we'll build up to writing some complicated programs. So do keep paying attention, and you'll see how you can easily write programs that solve puzzles. Okay, so let's get back to and now, oh, what I wanted to show was if I say member 2, 5, 10, 20, what do you expect? Failure. 2 is not a member of 5, 10, or 20. Okay, so let's go to our program again. Now let's add append. I'll just call it app. App empty list, L, app list H vertical bar T, L, H vertical bar R, if app TLR, right? Okay, awesome. And now we do SWIPL again. And now we do again. If you want to consult a series of files, you can also use square brackets and say simply fam.pl. So you can give a list of files that you want to consult all together. Now, what do we call it? mem.pl. Are you having trouble in seeing the video? Oh, it seems to be stuck. You're right. No, it's correct. It's current. I can see it on my other computer. Yeah, so it's working. So it might just be your bandwidth. Okay, so now we say append 1, 2, 3, comma 4, 5, comma x, bingo 1, 2, 3, 4, 5. But remember that we define in Prolog, we define relations. So now we can say append 1, 2. What will L be so that the result is 1, 2, 3, 4, 5? Can you tell me the answer, anyone? So see, L is an unbound variable. Excellent. See, 3, 4, 5. Very good. And then of course, I can leave the first part unbound as well. So I can say A 4, 5, 1, 2, 3, 4, 5. Right. And then as you would guess, anyone, what will A be? 1, 2, 3, of course. Okay, but now even better. What if I leave both unknown? So you see, what is happening? It's basically splitting up 1, 2, 3 in every possible way, such that if you put them together, it gives you 1, 2, 3. You see, the first answer is empty list A is empty, B is 1, 2, 3. Second answer is A is 1, B is 2, 3. Third answer is A is 1, 2, B is the list 3, and then 1, 2, 3, an empty list. Okay, and the execution mechanism is the same. So let me just show you the execution mechanism. I mean, run by hand. So we'll have to get the tablet out again. And let's see, now go back to OneNote. Okay, so we have this rule. So we'll keep this written here, but let's clear this up. So I hope you're following, right? Looks like you are, which is awesome because you're answering my questions. And as you can see, it is not very hard. You just have to follow carefully. And it's really wonderful. I mean, so I write all my code in Prolog, especially, if you have to compute something quick, then, very fast. I can write the code very quickly. Okay, so suppose my query is append 1, 2, 3, 4 A. How will I run this? I will say, okay, there are two rules. First rule doesn't match because empty list will not match with 1, 2. So the execution mechanism is the same as we saw for the family database. Try the first rule, except that now instead of having constants like John and Mary and all that stuff, you have lists. But lists must also match, right? So you're just performing matching. So 1, 2 list can never match with the empty list. So the first rule will fail. Go to the second rule. Match list 1, 2 with h const t. What will you get? H is 1 and t is the list 2. Wonderful. What will be the value of L? Match second argument 3, 4 with L, which is unbound. So L becomes 3, 4. What about the third argument? A is unbound. So what we're saying is A must have the pattern H vertical bar R. A must be a non-empty list whose head is H and whose tail is R, where H is 1, right? So H is 1, right? We saw H is 1 over here. So might as well this, right? H is 1. So you see what this is doing. It is saying if I append the list 1, 2 and 3, 4, then A will be a list that starts with 1 and the tail is something that is unknown, R. And then I go execute, right? I have to next replace with the body, and the body is append T, which is 2, L, which is 3, 4, R. And you can see that I have reduced the problem of appending 3, 4 to 1, 2 to appending 3, 4 to the list 2, and whatever result R I get, stick 1 in front. So you see, whatever I explained to you, that's exactly what is happening. And then, again, the base case will not match, will fail. Try the second case, and then now you will get R is 2 vertical bar. So now when you create, whenever you invoke a procedure again, then you rename all the variables. We'll put them primes. So this R becomes 2 vertical bar. Well, let's do it properly so as not to confuse you. So match the list 2 with H prime vertical bar T prime. So H prime becomes 2, T prime is empty, right? You're following? Because the tail of the list with a single element 2 is empty. L prime is, oops, you do get the, I don't know how I got it. I touched something. 3, 4, right? This 3, 4 and L prime. and then this R is bound to H prime R prime. R becomes H prime vertical bar R prime. Okay, you're following? So, and now I have to do append of T prime, which is empty. T prime is empty over here. L prime, which is 3, 4, and R prime, which is unknown. And now you see the base case will match. So this L will become 3, 4, and this L will become R prime, which means this R prime equals 3, 4. So we get R prime as 3, 4. And now my answer is the value of A, and I'm done. Success. What is the value of A? A equals 1 vertical bar R. What is R? R is 2 vertical bar right? So H prime is 2. This H prime is 2, right? Vertical bar R prime. And what is R prime? R prime is 3, 4. So this is really written in the head vertical bar tail notation. So this is really the list 1, 2, 3, 4. Okay. Okay, so we know append now. So I will, and so already you know actually quite a bit of powerful stuff that you can use for example, solving the n queens problem, which I will show you since we still have another 30 minutes. And I will also show you how to solve puzzles like send plus more equals money. Okay, so we'll write a program for solving. But before we do that, we need a variant of the member program, slight extension of the member program. Where did my member program go? Okay, I erased it, I think. Okay, never mind. Okay, so let's write member again. Member x comma x vertical bar t. So x is present in a list if it's present in the head, and member x y vertical bar t if mem x comma t. Right, it's the same code as before, except I shortened member to mem. What I want to do is to write a predicate. So in this case, it checks if x is present in a list. What I want to do is if x is present in a list, then delete it and leave the remaining elements in another list. Okay, so we'll call this predicate delete. Delete x. So if x is present in the head of the list and I delete it, I will be left with the tail. So now I'm producing an output. So the output has to be represented as a third argument. So you notice that, see, remember that you no longer have functions. There are no functions. They're all predicates. If you want to output something, then you have to add an argument where you compute the output. Okay. So delete x from x vertical bar t, where x is the head and t is the tail. Then obviously what is left is the tail. But delete recursively x y vertical bar t, comma something if recursively delete x from t to get r. And how will you get your final output? Anyone? I need to keep the y, right? Because y is not deleted. Y vertical bar r, right? Does that make sense? So to delete x from y vertical bar t, I recursively delete X from T to get R, but I need to copy the Y, right? Y vertical bar R, yeah, very good. Okay, so now let's see delete, and sometimes it's called select. Okay, so we'll call it, instead of delete, we'll call it select, but it's the same. So you notice that member and select are identical if I drop the third argument of select. So I'm just renaming it to select, that's all. Okay, so now I can quickly run select for you. Okay, attach. Okay, so we'll just copy member. Okay, and then oh, now we can't put underscore because I'm returning it, I'm reusing it. So it's the same code that I wrote just now on the tablet. Select X, Y, T, X, T, R. Yeah, okay. And now I can. Right, you see the code, SWIPL. Again, so consult mem. And now if I say select X, comma, and 2030, comma, Y. Well, first do a simple case, 20, comma, 10, 20, 30, comma, Y. What do you expect in Y? See, right? It deleted the 20 and we only got 1030. But the most interesting case of select is when you use append or member to compute multiple answers, like we did mem X, or no, we call it member X 10, 20, 30. It's called a generator. So we're generating multiple potential values for X. So likewise for select X 10, 20, 30, comma, Y. What do you expect? It'll bind X to 10 and Y to 20, 30. If I hit semicolon, what will happen? Anyone? Any guesses? Okay, see the answer? Now it bound X to 20 and put 1030 in the list. Remaining elements, right? Deleted 20. And what's the third answer you will get? Now you should be able to guess. Third answer. Yeah, 30 and 1020. And then no answers. Okay, awesome. So such usage of select and member is we say that they are generators. Okay. So one more program that I want to write. Okay, so I need to teach you how to do arithmetic next. So we're on track, and within another 25 minutes or so, we'll be, coming to solving things like send plus more equals money. Okay, so how do we do arithmetic in Prolog, or arithmetic computations in Prolog? So for that, you have to use something special. So again, detach. Okay, so if you want to compute arithmetic expressions, then you will say something like use something called is. You will say x is 2 plus 3. So if you say x is 2 plus 3, it will compute x to be 5. So you can have any complicated expression. X is 2 plus 3 times 10, and it will tell you x equals 32. Okay, 3 times 10, 30 plus 2, and so on. So what x, so the general format is, but you can also do things like 5 is 2 plus 3. It'll say yes. And it's obvious, right? What's happening? It's computing 2 plus 3, matching it with 5. You can say 6 is 2 plus 3. Now what will happen? Any guesses? It'll fail. It'll say no. Because 2 plus 3 is not 6. Okay. So what it does is, so when you have x is some arithmetic expression, it evaluate the expression. If there are unbound variables in the arithmetic expression, it will abort your program. So you cannot have variables present. I mean, if they are, they must be bound. Then unifies. See, unifies is different from assigns. Unifies means it will look at the value of x and match it with the value of the value that you got as a result of evaluating the arithmetic expression. Unifies x with result of that arithmetic expression. If the two match, now if x is unbound, it's always going to match. But if x is bound, then it must be equal or else it will fail. So every predicate, every built-in in Prolog has to be set up like a predicate. Right? So is basically turns arithmetic expression into sort of like a predicate. It's a predicate version of evaluation. Now you would expect that if I say x equals 5, so equals is the unification operator, which will just bind x to 5. Okay, but you can't say x equals 5, x equals 3. He'll say no, false. Because it's saying x is assigned 5, x is unbound here. But when you come here, x is bound to 5. And now you're saying 5 equals 3. So this is not assignment operator. This is a unifying matching operator. So when you match an unbound variable to a constant, then that unbound variable is assigned a value. But once you have done it once, it's got a value. You can only match it with other values. You cannot change it. Okay. But if I write x equals 5, x is 2 plus y, what do you expect? You would expect that, hey, should be able to tell me y is 3. But unfortunately, in this format, it does not. It aborts. It says, oh, y is unbound. I cannot perform arithmetic with unbound variable. There are extensions of Prolog that will treat this as a constraint and solve for y, because it knows x is 5 and y can be computed, so it will compute the value of y. But we're not going to bother with that. Okay. Now that we know arithmetic, we know so we can write let's say a program. Okay, we'll write a simple program to sum the elements of all the elements in a list. Okay, so what I want is something like sum of, oh, if I have a query, sum 10, it should come back and tell me A equals 60. How will you write such a program? You'll write it recursively, right? Because basically, otherwise you'll need a for loop or a while loop. So how will we write this code? We will say, okay, so follow me along. Sum of recursively, right? First argument is a list. So we'll have to have two cases, empty list and non-empty list. Empty list, the answer, the sum is 0. If it's a non-empty list, H const T sum, then recursively find the sum of T in S1. And then how will you compute the final answer? Anyone? So suppose magically I sum up the tail of the list to sum to S1, sum up to S1. All I have to do is to add the H, right, to S1. So I'll write S, which is my final answer, S is S1 plus H, and I'm done. Right, you got it? Okay, so with this now, okay, I can also, let's write one more program quickly, which is the insertion sort. So insertion sort, first we write in, you know how insertion sort is. Basically, you start with an empty list, you look at the first element of the list and insert it in the right place. So you kind of keep a partial list which is sorted and you keep looking at your, right? So suppose I have 3, 1, 2. Then I'll start with the empty list. I'll say, let's place 3 at the right place. So I get the list 3. Then I say, oh, let's put 1 at the right place. I'll get 1, 3, 1, 3. Then I say, let's put 2 at the right place. And I'll insert it in the middle of 1 and 3. That's how it works. So how will we write insertion sort? Let me write that. And then I will show you the code for send plus more equals money, how to solve that puzzle. So you already know, see, in just 2 hours or less, you have, you should be able to write code for send plus more equals money, which is quite, right, outstanding. However, I mean, we're touching only the tip of the iceberg. There's a lot more to learn. So insert, I want to insert X if I have the empty list. Then I get the single. So that's a base case. I reach the end of the list, or as the list is empty, then X, insert X, Y, vertical bar T, right? If X is less than equal to Y, then where does X go? Assuming that's ascending order, put X in front of Y. So this pattern, X, Y, vertical bar T, means first 2 elements are X and Y, rest of the list is T. Anything that comes after the vertical bar means rest of the list. So, and that's it, right? If X is less than equal to Y, then just put it before Y. Otherwise, X is greater than Y, in which case, what will you do? Recursively insert X in T to obtain R, and then stick Y in front of R, because we have to keep Y. We cannot lose Y in the output. So this is the output. And now, so this is inserting an element X in a list that is sorted in its proper place. Okay, so now I want to insertion sort, I sort. So I will start with a list L and I will obtain the resulting list LR. How do you do that? You call I sort, but with 3 arguments. L, we start with the empty list and Okay, so I sort with 2 arguments is different from I sort with 3 arguments. Prolog will have no difficulty in figuring that out. And now we have to define I sort with 3 arguments. So so this empty list is where you accumulate your answer. Okay, so if my list is empty, then whatever I have here is my final answer. Otherwise, I sort H vertical bar T R, or let's call this S, and then the result R. So you recursively, or you insert H in S in the right place to obtain S1. So S is sorted. Oops, what happened here? Okay. Okay, so insert H in S, right? S is my sorted partial list that I'm carrying along. So use this insert to insert head of this list in S. Initially it was empty. Okay, to get S1. And then what will you do? You will recursively call I sort with tail of the list and this new updated list S1 to obtain R. Does that make sense? Okay, so again, you have to do a little bit of thinking, but you can write these kind of programs. Okay, so let me now write the program for send more money. Actually, I will show it to you. I already have it. One line by line, we'll go through it, and also program for writing n queens. Okay, so yeah, it registered. Okay, so crypt.text. This is the program which says, so you know the puzzle send plus more equals money. Trying to increase the font size. Let's see. Okay, anyway, we can. Oh. Yeah, you can. VI. Sorry. Okay, there it is. Yeah. So there are. So the puzzle basically says you have send plus more equal money, and you have to find values for S, E, N, D, M, O, R, and Y, such that send plus more adds up to money. And we'll use the select. So we'll write a program called solve with 8 variables S, E, N, D, M, O, R, Y. So we know that since M is over here, M must hold a carry. So M is equal to 1. So we kind of assign that. Okay. And then the rest is so for solving these kind of puzzle-like programs, you use what is called generate and test. Generate and test. Which means so it's like solving the Sudoku puzzle. You can generate a configuration and then check that it follows Sudoku puzzle rules or not. Okay. So same thing here. It's like a puzzle. So there are many combinations of digits for S, send plus more equals money. We're going to try them out, but we have to do it in an efficient way, clever way. So what we're going to do is set M to 1 because we know M is 1. Then we will start from the right hand side. We'll say, well, let's select D from the remaining digits. What are the remaining digits? 0, no 1 because 1 is already been used. And also know that each digit can be used only once. So you cannot have S and O have the same value. But then it is very easy. So each digit has to be unique. So we select, remember the select we saw? Select D from this bucket of digits, 0 through 9 minus 1. And leave the remaining digits in L1. And then I will select E. So I'm trying to first solve this column. Select E from L1, right? So L1 will contain the digit, all the digits from this bucket minus what we selected for D. Leave the remaining digits in L2. Now we will compute for Y. Okay. So we can compute Y. Once we know D and E, right? We selected D and E, we compute. So what is Y? Y is D plus E mod 10. But also I might have a carry, which may be 0 or 1. So I compute the carry number 1. So there are carries here. So this carry is C1, 2. Yes, I don't have enough space, but maybe I should add it. Okay. And then carry C3. Okay, so C3. So I have to potentially might have carries also. So what is the carry going to be? The carry C1 is going to be D plus E div 10. This is how you write div in Prolog. Basically the quotient, right? Mod is the remainder. And then once you have carry C1, I need to make sure that the digit for Y is deleted from L2. So you select Y from L2, delete it from L2 to get the remaining digits in L3. You see, that's important because you don't want you want Y to be unique also. So you have to make sure if Y is not present in L2, the digit that we computed, then this select will fail and it will try something else. So see how you use backtracking to generate different possibilities. Okay, so it's actually quite brilliant. I mean, the way whole thing works. So then you go and select N, right? We next select the next column, solve the next column, select N, select R. So select N from L3, leave the remaining digits in L4. Select R from L4, leave the remaining digits in L5. And then you can compute E. What is E? E is C1 plus N plus R, mod 10. So N plus R plus C1 mod 10. And what is the carry C2? It is N plus R plus C1 div 10, backslash backslash 10. And next we have to go to column number 3. Since remember E we already selected. So when we compute this E over here, right, because there was an E here, we don't have to delete it again. It's already chosen uniquely. So next I have to, again, E, you don't have to select because it's already bound. So next you select O, right? Select O. So we call select O L5, L6, compute the N. And this time N is E plus O plus C2 mod 10. And you get the hang of it, right? You get the code. And then we have code for select over here. And so now we can actually run this code. Okay, so more crypt. Let's see, hopefully it will run. Okay, so SWIPL. Oh. Oh, okay, it's giving me some. What's the problem here? Oh, because I put this C3, C2, C1. Okay. Okay, so crypt. throw. Why is it giving? Oh, because it's called crypt.txt, not crypt.pl. Okay, got it. See, it's working. And now if I say, what was my query? All, right? You can see it's a little bit A. I'll have to do A. A will be bound to the list SENDMORY, and here it is the solution. Okay, so it is SEND, only one solution. So you can see that it is, let's copy this in the file. Okay, and then we go to V. That's what it generated. So so let's see, we can see SEND. So 9567 MORY. So MORE 108 E is 5. And the result is one. O, what is O? SEND MO is 0. N is 6. E is 5. Hopefully it adds up. I think it's correct solution. And Y is 2. Yeah, okay. So 7 plus 5 is 12. 1, 6 plus 8, 15, 5. 1 plus 5 is 6. And 9 plus 1 is 10, right? Okay, so it works. So you can see how you can write these kind of programs. So if you were to write the program for solving Sudoku, all you have to do is to use select and generate the values for the rows, values for the columns, and values for the 3x3 grids, and check that they're consistent. And you can basically solve it very quickly. Okay. Okay, so I think I am coming up to the hour, and I just want to show you one more piece of code, and that is for solving the n queens problem. So what's the n queens problem? So the n queens problem says that you have an n by n chessboard, and which you have to place n queens, and no two queens should kill each other. Okay. So okay, so I don't know why it says select instead of select, but doesn't matter. So, and you can see the code is so short, and where gen is nothing but given a number n, it will generate. So let's try this out. SWIPL. Ah. Okay, so if I see gen, you can see what gen does. See, if you give gen 8, comma 8, it will generate numbers from 1 through 8. Okay. So that's what gen does. And you can, I can share this code and you can actually try it out. Okay, so let's put it on the chat. How do I get to the, yeah, there it is, chat. Any questions? Yeah, the video will be posted. I see. Okay. So that's n queens. And then let me also post the code for crypt arithmetic. It will be done in another few minutes. Oh. Okay, post here. You can try it out. Okay, so let's just quickly look at n queens. So what it does is, so you call predicate queen n comma q. Okay, so n is the number of queens you want to place. So obviously, if you have 10 queens, for example, then you assume a 10 by 10 board. Q will give you a list of size 10. Okay, and I'll run it and show you, explain you the answer. So SWIPL. Okay, so if let's run queens, queen 8 comma q. Okay, so what this is saying is that in column number 1, the queen has been placed in the 4th row. In column number 2, the queen has been placed in the 2nd row. In column number 3, the queen has been placed in the 7th row. Column number 4, queen has been placed in the 3rd row, and so on. And you can actually, it'll give you all 92 configurations if you keep hitting semicolon. And you can see it's such a short code. So what this does is it says, okay, generate a list L from 1 to n in gen n comma L. Then you assume that there is an empty board, empty list, and we'll place, just like we did in sort, we'll place queens from the list L, this number from 1 through n, one by one, into the empty board to obtain the result Q. And how does place queen work? If you have an empty board, I mean, if you ran out of queens to place, first argument, then this is my partial answer that I'm building, already has the final answer. Copy it over. Otherwise, I am in the middle. I have my list of queens I still have to place in L. This is my partial board, and this is my resulting board. Select a queen Q from L, and you are left with remaining queens. Then you check that the queen Q can be placed in the the partial board safely. Okay, so the safe will check for that. And then once you have done that check, then place the remaining queens in Q added to the partial board. So if Q is safe, you add it to the partial board, and now you continue placing queens, and you compute your final answer R. What does safe mean? Okay, so if the empty board is a safe board, okay, so safe means that you have a partial board and no two queens attack here each other. And you know that when do two queens attack? Either they're in the same column or in the same row or in the same diagonal. Now you notice that by representing this problem where you have 8 queens and representing it as a list, you know that there cannot be 2 queens in the same row or the same column, right? Because this number means that there is only 1 queen in the 4th row. And since number 4 can occur only once, we know that no other place will have 4. So see how cleverly we represented the problem, and so that we don't have to. We are guaranteed that there'll be no 2 queens in the same row or the same columns. All we have to check for is the diagonal. Now in a board, When do you know that two queens will kill each other on a diagonal? So let's put it up. So let's make a 5x5 board. Okay, so two queens will kill each other in a diagonal if, okay, so I numbered that. So let's say this will be something, something, this will be 3, right? Let's say the queen is here. So this will be 1, 3, and let's say the queen, doesn't matter, is here also. Well, it cannot be, it doesn't matter. Here it is in 5 position, right? So you see that this is row, column number 1, column number 2, column number 3, column number 4, column number 5. Two queens will be in the same diagonal if their difference of rows equals their difference of column, right? You see 4 minus 2 equals 5 minus 3. So they're in the same diagonal. It's like, basic coordinate geometry, right? Analytical geometry. And so that's what you have to check. And that's what this code does. It basically keeps track of, starts with column number 1. Okay, checks that the queen X does not attack anything between 1 and Y. And it basically computes the difference of row and the difference of column. So I'm not going to go into this code. And then it checks for the safety of the board. I mean, you can run it and follow it if you wish. I already posted it. And so that's it. I mean, you're basically placing the queens iteratively in a safe manner until all the queens are placed. Okay, so this is probably a little bit complicated program that I don't expect you to be able to write, given just you got a 2-hour exposure to this kind of thing, but it gives you an idea as to what kind of problems can be solved. However, next workshop, which will be Wednesday, same time, 1 p.m., we will see it will be hopefully somewhat simpler because we'll be mostly dealing with just we won't have lists, for example. So I wanted you to learn how to use data structures, because sometimes you do need them, but otherwise you'll mostly be modeling database type thing, where we'll see how you add common sense knowledge. We'll add negation to Prolog, because and we'll talk about what is involved in modeling common sense reasoning. So next class at 1 p.m. we will study answer set programming. We'll build upon from here. So this is very critical. We'll build from here, and then we'll see how you can simulate common sense reasoning. And then the hackathon on Friday. Okay, all right. Any questions that you folks may have? So video will be made available. I'll send it to. Oh, okay. Also want to acknowledge the AI Society folks. Rushi, who was wonderful in setting all these things up. The hackathon is virtual. Yes, everything is virtual. All the talks, everything will be virtual. There are some interesting talks, including on explainable AI, which is, given a machine learning model, which is typically a black box, how do you extract the rules from this model so that you can understand the bias in the model, right? So that's a huge thing these days. So we'll have a talk on that. We'll have a talk on how to use common sense reasoning, and you'll be able to actually follow it. How can we use answer set programming for building an autonomous vehicle? Because if you think about driving is a common sense reasoning activity, right? I mean, it's actually control of the car that is much harder to learn than actually knowing that when I come to a green light or red light, I have to brake, or if I see a road and I have to go someplace and my destination is, or how to, I have to change lanes if I have something in front of me that is stopped, right? That's all that is common sense. How can we model a driver's mind using common sense reasoning and answer set programming? So there'll be another talk on that day on that. So it should be quite interesting. So as I said, you can see that if we can automate common sense reasoning, the human thought process, then you can automate anything, including autonomous driving, right? Build autonomous vehicles following that logic. So the hackathon is virtual, yes, and any questions? But the video will be available through Rushi, and I wanted to acknowledge the help of AI Society in organizing everything. Okay, thank you. If there aren't any questions, we will stop here. And hopefully the video has been recording. Okay, awesome. Thank you then. Bye-bye. We'll see you at 1 on Wednesday, so don't miss that. Leave from here also.